Hello and welcome to the class notes on Chapter 15 of our AP Statistics textbook, Pearson textbook. This going through the notes here assumes that you've already read the Chapter 15 of the book. So I can go through a little bit faster and work a couple problems, but not hit every single little detail. So make sure you're reading Chapter 15 of the book before watching this video. All right, so you should have read about random variables. We have discrete and continuous. Discrete are things like how many chairs and how many pencils and how many people. Continuous are things that have decimals to them, and any possibility, any combination or any number is possible. I weigh 83.26 kilograms, right, or something like that. So a lot of times weight and speed and some kind of measurements like with distance, things like that are continuous. Discrete is more either it happens or it doesn't. So, if we got 5 things happen or 1 thing happens, or you get a number for it, right? So discrete versus continuous, make sure you understand that first. If you don't, go look it up right now and come back to the video. All right. Expected value, we talk about expected value a lot from now on. And we're going to use expected value interchangeably with the mean. So we've talked about the mean before being, just an average. We've also looked at the mean of a normal curve. But now we're kind of looking at discrete variables, right? So now we're talking about discrete variables and how the expected value you get out of that, we're just going to call it the mean. Basically, it's the average, it's the center. It's what you think is the typical average thing that's going to happen, even though you have variation going on. So when it's discrete, like normally we would just take our total things, like whatever the values are. I don't know. I got in this car, I see 3 people riding in it. That car has 1, another car has 5, another car has 3. And, if you were to add those up and then you wanted an average number of people in a car, you would just add them up and divide by how many cars you observed. But now we're going to expand it a little bit and make it into a little more deeper and give you more options, right? So what if it's not equal chance, right? What if the chances are different? What the probabilities of a certain thing happening are different. So the formula you see down here is the mean equals the expected value of x, whatever the discrete thing is you're looking for. So what you do is you take the value of that times the probability of that happening. It seems maybe a little weird, but it's really just a weighted average. So you're still dividing by how many you have, but each one has a little bit different weight. So maybe instead of saying, oh, I got 10 things, you might, and dividing by 10, you might say, well, this particular value has a weight of 4 of those 10 things, and this other thing has a weight of, 1 of those 10 things, etc., right? So you're multiplying by that probability. The dividing by 10 still comes in there, but it's like saying, well, I got, more of them. Maybe I'll go into more detail on that later. Let's take a look at an example and then hopefully it'll make more sense. Okay, so that's what we're doing. And then the standard deviation of it, that's, we looked at the mean. So if you want to look at standard deviation of it, then you should really think about variance first for all these problems we're doing today. So variance comes first, and then you can always take the square root of variance to get your standard deviation. So just like standard deviation before, we said, oh, okay, let's take our mean and subtract it from all of our values, right? So if our mean was 10 and my value was 12, I'd just take 12 minus 10 and get the difference. So you have a whole bunch of differences for every single point in your set and squared. But again, instead of like dividing this by how many I have total, which we did in the past, we are going to multiply by the probability of each event as we go along. Because when you divide by one number, you're saying that all of them are equally likely to happen. But now we're saying we're going to allow for the chance that one thing has a different probability of happening than another. So we include that probability. And by doing so, that automatically brings in the divider number, right? Dividing by 10 or dividing by 5 or whatever you're dividing by. Normally, it comes into the probability. Okay, so that's what we're going to do. And again, you just take the square root of variance to get your standard deviation, which would be useful. Okay, so let's look at an example. This is an APGAR score. When babies are newly born, they test them out through these things to see, if they're doing well as a newborn baby. So how's their activity, their muscle tone, their pulse, their appearance, their skin color, respiration, and do they have good reflexes, and do they react normally, right? So you can give them a point, either a 0 points for it looks bad, 1 point for somewhere in the middle, and then 2 points for they look great, right? Okay. So, and they're hoping for a good score on this. If a baby gets 10 out of 10, then they're lively and active, and their pulse is perfect, right? That's what they want. So it's a value from 0 to 10, 5 times up to 2 points each. Okay. So through experience, though, the hospital has done this over and over and over again, and they've collected data, so they know what to expect. They don't expect every single baby to get a 10, and they definitely don't want every baby to have low numbers like a 0. So they want to know, well, what's normal, like what do most babies have as their score, right? So they can kind of have a guide to say, well, if it gets below this number, then we're going to really, give it special attention, or if it's, that kind of thing. So they want to just know what's normal, right? And kind of have an idea of the spread of it, getting a standard deviation. Okay, so here's a problem. Here's the data they've collected. So for the APGAR test, over tons and tons and tons of babies that they delivered, and they've done the APGAR test on, and they have records for this. They've put it all together, and they said, okay, only less than 1%, like 0.1% of the time, we'll get a baby that has zeros all the way across, and they get a 0 score total, right? 0.6% of the time, we'll have a baby with a score of 1, etc. So you can see that most babies, like there's 1% or sorry, 9, almost 10% that have a 7, and 32%, almost 32% with an 8, etc. But again, only 5% get a 10 out of 10. So most of it's like right in this 7, 8, 9. I can kind of see that's where the average is, but we're going to calculate what that average really is, okay, using a weighted average. If you'd like to try this on your own right now, pause the video and then calculate your mean and your standard deviation using these formulas. So we're going to use this formula right here for the mean, and we're going to use this formula here for standard deviation, well, variance first, and then get your standard deviation. Okay, so try that, pause the video, and then come back. Okay, so here comes the solution then. So you can see it's a big long list of numbers, right? Because the formulas have the sum of all these together, and each one of these has a different probability going on with a different value that's associated with it. I can't just add these up and divide by 11, because there's 11 numbers, right? I can't just add them up, divide by 11, doesn't make any sense, because each one doesn't have the same probability of happening. So the 0 value has a 0.001 probability of happening. So I multiply those out. What that's doing is weighting the 0, right? How much in the total do I want the 0 to be included, right? And it's very little. It's only 0.001 of the total. You'll notice all these probabilities will add up to 100%, right? Or 1. So how much does the value of 1 contribute to the total, right? Well, it's only 0.006. So when you multiply those out, it contributes very little, right? A value of 2, 0.007, etc. So, an 8 times 0.319 is going to contribute a lot more than a 0.006 times 1, right? Which you would expect, because these have more weight, so they should be represented more in the total. So when you do that, you're going to get 8.128 for your average. So this is your expected value. Again, it's expected value, not what really is going to happen, right? It's just what we expect on average to happen. To do your variance, you follow the formula, you subtract your mean. So my mean was 8.12. 8. So you'll see that along in every single one of these. Take the 0 minus that, square it, times its probability. Take the 1 minus that, square it, times that probability, right? So again, we're using these probabilities to weight how far away, right? Like when you subtract these, you're getting a difference. So when you multiply the probability times that difference, you're kind of weighting the difference. Like how much weight should this difference include in my variation, right? So you do them all. I just did a little dot, dot, dot here because I didn't need to write them all out. I showed you how it worked from the first, the second, and the last one. And then when you put all that together, you get a variance of 2.15. You take the square root of that, and you get a standard deviation of 1.47. So on average, most babies will be around 8.13 for their APGAR test, right about 8. And there's a standard deviation of about 1.5, right? So, and you could use this in a normal curve as well and just say, okay, so if I go down 3, down to 5, and I go up to 10, right? If I go 3 up, I'm going to be at 10, right? So in general, like you can come up with probabilities of it. Now, I have the probabilities right in front of me. So if somebody said, what's the probability that someone gets a baby has an APGAR test between 5 and 10, you would just add these probabilities up that are right in front of you. There's no reason to go to a normal curve or anything like that because we don't really even know this is normal, to be honest, right? So just use the probabilities right in front of you and just add them up. All right, the next thing is transformations. So what happens to means and standard deviations then when we add and subtract values? We've seen this a little bit before. When you add or subtract a constant number from a data set, like to every single value, then the mean will go up by that amount or down by that same amount. But the variation doesn't change, right? It's just like saying, if I take this and I shift it up to here, right? And this center has been raised up, but the actual distance or the actual range hasn't changed any, right? So when you add and subtract a value, the mean increases, but the variance does not. We've seen that before. When I multiply all like values by a number or divide, multiply or divide, your mean will get multiplied by that value, which we've seen before, and your standard deviation will as well. Okay, keep in mind it's a little tricky. Sometimes they'll ask for variance. The variance changes by that multiplier or that divider squared, because remember, it's standard deviation that actually is the one that's getting multiplied. So standard deviation will increase or decrease by the same multiplier, but the variance is that multiplier squared. So be careful with that one right there. All right, let's look at that in action. I think these are always so much better just to look at a problem. Okay, so we got a Lexus dealer, has a bunch of employees. They have a mean of $42,000, standard deviation of 3,500. And we want to know, well, let's say the company decides to increase everybody's salary by $1,000. So everybody gets an extra $1,000 in their salary every year. Okay, so then how does the mean and the standard deviation change? Think about that, and then you can do the next one too. If everyone receives a 3% increase in salary, so the first one is you're adding 1,000 to everybody's salary. The second one is you're increasing everybody's salary by 3%. So that's a multiplier. All right, so if you want to solve this on your own first, pause the video, and then you can come back and look at the solution. Of course, you're using these formulas here, right? Okay, here we go with answers. For the mean of this first one, to increase by 1,000. If everybody increases by the 1,000, that means the average is going to increase by 1,000 as well. The standard deviation will stay the same. Remember, the whole set moves up together, so the range doesn't change. The minimum and the maximum are relatively the same distance away from each other because they both went up by 1,000. Okay, so that one stays the same. For part B, when you're multiplying by 1.03, the mean will change. It'll increase, of course. So everybody gets a 3% increase. So I used 1.03 to increase their salary. to 43,260. And when you're doing variance, remember it's 1.03 squared times the 3,500 standard deviation. Yeah. Oh, this is not correct because I should because this is standard deviation up here. Sorry, this is not correct. This should be just 1.03 because the 3,500 is standard deviation. So this should immediately went into standard deviation. Honk. And then this, I don't think, this is not right then, I don't think. So it's just 3,500 times 1.03, and that will give you your standard deviation. If you wanted variance, then you'd have to square it, right? You'd have to square that. Or take this 1.03 squared times the 3,500 to get variance, right? So kind of, yeah, so I was mixing variance and standard deviation there, okay? So sorry about that. All right, so next, that was all kind of working with discrete variables a little bit on this first part especially. This is what you consider discrete variables and the probabilities that go along with those. Each one's weighted. But now we're going to focus more on continuous data, right? Continuous data. So if you have continuous data, we always want, if you're going to do any work with continuous data, you need to make sure that the events are independent, and you need to make sure that they're all in normal in shape. And you have to think about this ahead of time, especially like on a free response question. You need to be writing this out saying, I checked it's normal, I checked that these are independent of each other, and so I can continue to do the work. We're going to see that this is kind of really interesting and very useful, actually, because you can start putting things together, which the real world usually have a lot of things that get put together. If you're working at Amazon and you're shipping out boxes, and they're talking about weight, you have the item that goes into the box, you have the packing material that goes in the box, and then you have the box itself that has weight. So if you want to put all those together, then how do you do that, right? Because they're three different things with three different means and three different standard deviations. So how does that all go together? Well, that's what this is all about here. So when you have different means, and again, if you have independent situations and situations that are normal in shape, then you can go ahead and add those means or subtract those means depending on what's going on. For the variance and the standard deviation, it's a little bit weird, but we'll try to maybe talk about it more in class and stuff. But whenever you want to add or subtract a couple of sets together, like the weight of a box and the weight of the content that went in it, and you want a total weight of a box, you can add their variances together. You can't add the standard deviations. It doesn't work. You have to add the variances together. So it's like standard deviation squared plus standard deviation squared. And the weird part, which we need to talk about, is what if you're subtracting in your thing? Like, let's say I had a big, I don't know, a big thing of Skittles or M&Ms or something, and I have two of them, let's say. So I'm gonna like add them together, but then after I add them together, I'm gonna take a big handful out and I'm gonna scoop it out, right? So you're subtracting something from a total. So the total itself had its own mean, and then the handful of M&Ms that I pulled out had a mean as well, right? So if I did it again and again, you might get, a little bit bigger or a little bit smaller of a handful that you're removing. So the means will just subtract, but the variances will actually add. So it's a little weird, but if you think about it, it makes sense. Every time you do something or you put things together, whether you're adding or subtracting them, you're going to get more variation. You're going to get more variation, right? The more things that happen, the more that plays into it, right? I might get a big box with an extra heavy box today with less packing material, or I might get a bunch of packing material next time with a box that weighs less, or I'm just trying to give some examples. Maybe the Skittles example, like if maybe the big box of Skittles I have has a little bit more in it than usual, but the handful I removed had a little bit less than usual, or a little bit more than usual, right? Or the big box had a little bit smaller amount of Skittles in the big box than normal, and my handful had a little bit less than normal in it, right? So it's just more variation. So you think about all the different combinations I could have, right? Big plus big, big plus small, small plus big, small plus small. There's a lot more variation going on every time you combine something. So whether you're adding or subtracting the means, the variances will always add together. So I put that in purple right there. It's always the sum of the variances, always. All right, let's look at an example. It's a good example. We got a 4x1 swim team at ASIJ, girls swim team. School record is 3 minutes and 40 seconds. I don't know if that's true. I just made it up. And we have 4 different people that are going to do the relay together, and they're hoping to break the school record. What's the probability that they're going to be able to break it? Right? This is a good question, very realistic. You want to know what's our chances of breaking this thing. So what you do is just, well, actually, I'll let you maybe try it on your own using these formulas, right? And then pause the video, come back, and I'll give you the answer when you get back. Okay, so here is the solution. I'm going to scroll down, sorry. Started to go right into it before. So what do? Well, to get the average, you just add all the averages, right? I mean, Yui swims this fast and Dana swims this fast, et cetera, et cetera. So together, after everybody's done their 100 meters, basically you're just adding all these up. So that's what we do. We just add all the means up and we get a total mean. Again, is this the truth? No, it's just an expected value. It's something we expect their time to be around, right? On average. If they did a relay again and again and again, then this would be their average time, right? Together, right? Obviously. Okay, so for variance then, to find out the standard deviation, because maybe Yui swims really fast one day on this particular day, but the other 3 swim slower than normal. Or maybe they all swim faster than normal and they do break the record. Or maybe they all swim slower than normal and they have a lot of variation. So every single person has their own variation going on. So when you put them together, you get a lot of variation, right? I mean, there's a lot of options and ways that people could get faster or slower on any particular day when they're swimming together. Okay, so this is what you do, right? So you take the variances. So you have to square these each and then add them together to get the variance of the total set. And to get the standard deviation, of course, you just take the square root of that and you get your standard deviation. So now this is powerful because I have a mean and a standard deviation that I can use on a normal curve, and I can do all the probabilities I want. Now, of course, before I did any of this, I should have checked to say, are all these people independent of each other? The way the speed that Yui swims, is that going to affect how fast Asako swims? We're just assuming they're all swimming as fast as they possibly can. Now there is something to be said, like, okay, if everybody else is having a good day, then maybe the last person steps up and has a unusually good day as well. There's something about that, but we're just going to assume these are all independent, and that every single one of these people have a normal curve, a normal shape to their swim times. All right. So if that's all true, then I can use the mean and the standard deviation, and I can use a normal curve, which becomes powerful then. So if I want to know what's the probability they're going to break the school record, that means they need to get less than 220 seconds, because the school record was 220 seconds. So I just use my normal CDF on my calculator like we used to, go from negative infinity up to 220, put in your mean and your standard deviation for this situation, and you get 44.6%. So they have a really good chance of breaking the record this year, especially if they do more than one meet, right? This is just the probability for one meet, just a one-time shot, right? So if they do it more again and again, then they even have a better chance. All right, here's a couple more problems. I won't spend a lot of time on it, but it's very similar to what we just did. Let's say you want to know what the probability that a woman's height, a randomly chosen woman, will be taller than a randomly chosen man. Here's the mean and standard deviations for both. And same thing down here, we have another type of problem like that. This one's like commuting to work. So how much gas does it take to commute to work? Well, going to work, this Amanda leaves early and she doesn't use as much gas, but coming home from work, she's always in rush hour traffic and she uses more gas. But she wants to know, going to work and returning from work as a total, what's the probability that she's going to use more than 25 liters of gas, right? And there's the stats for each one. In all of these, we're assuming they're independent, like the men and the women heights are independent. We're assuming the liters of gas used going to work and liters of gas returning from work are independent events. They don't affect each other. And we're also assuming that each of these are normal in shape. Normal, 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 right? So two different problems here, but I'm just kind of talking about all of them together. All right, so pause the video if you want to do them yourself first. Give it a try. It's always a good idea. All right, here's the solution. Here we go. So you can see this case, I'm going to subtract. The trick to this one is that having a woman's height higher than a man's height is the same thing as a woman's height minus a man's height being greater than 0. So what that does is put it together for us and gives us a numerical value that we can then do the probability with. This is really a big key to this problem, which you're going to have to be able to do in other problems in the future. So take a note of that. All right, and then we just calculate the mean. We just subtract now. So now we're subtracting, right? The height of the woman minus the height of the man. Subtract, you get a -8 as your expected value. Your mean or your expected value is -8. Do your variance, so you square the standard deviation, add them together, and then take the square root to get your standard deviation of 10. Put that in the normal curve on your calculator, and you get a 21.2% chance that you'll find a woman that's taller than a man if you randomly select each, right? Now we got the gas problem, same work. This one is just addition, same work. You add your means, make sure you're adding variances, not standard deviation, put it in the normal curve, and you get your probability. So this is a really low percentage chance that she's going to use more than 25 liters of gas. Maybe she was worried about running out of gas on the way home from work, and that would cause a lot of problems. So she doesn't have to worry because it's a really, really low chance. Okay, so the only last thing is just what can go wrong, right? So I've said it many times in this video, but just always check. Make sure if you're going to use a normal curve and you're going to add and subtract variances and means that they are independent and they have to be normal in shape, right? So this normality assumption and the independence. And there's nothing specific you're doing. You just have to check. You just have to say, yes, there's no reason to believe that one of these affects the other. And I do have every reason to believe that, the height of a person is a normal in shape, right? You just have to acknowledge these two things, and then you can go ahead and use all these formulas for addition and subtraction of continuous random variables. All right, that's the video. Thank you very much.